This is section 2.1, Introduction to Chance Models. So as always, pause and look at those learning objectives. We're going to start with a reminder of unusual values. So we talked about this back in chapter 1, but if we have a symmetric data set that looks kind of like a normal curve, then about 68% of our observations are within one SE of the average. 95% of the observations are within 2 standard deviations of the average, and 99.7% will be within 3 standard deviations of the average. And you can see this nice graphic to remind us. What this means then is if we get something that's out in the tails, past that 2 standard deviations away or 2 standard deviations away this way, we're going to say, oh, that only happens about 5% of the time, and to us we're going to say that's surprising. And if you get something more than 3 standard deviations away, that only happens like 0.3% of the time. So that would be really, really surprising. Okay, so the thing that you need to remember for everything in this class is that we're going to call something surprising or unusual if it happens less than 5% of the time in the long run. So if we have symmetric data close to normal curve, how many standard deviations do we have to be from the average to count as unusual? Well, 2 standard deviations. Because it says if it happens less than 5% of the time, so less than 5% of the time would be this 2 standard deviations away. So some official terminology. A population is the entire group of individuals that we're interested in. Or sometimes if we're doing chance processes, it would be if you kept doing the chance process like an infinite number of times. So that population can be your outcomes from doing a chance process infinitely many times. So like if you want to flip a coin, if you could flip a coin infinitely many times, that would be your population. The parameter is a number that summarizes your population or your random process. So usually we can't collect data from every individual in a given population. It's too expensive, time consuming, etc. So instead of collecting data on every subject in the population, we collect data on just a smaller subset of the population called a sample. So the sample would be a smaller group of the population that we're collecting data on. The statistic is a number that summarizes the data we collect in our sample. And when I say summarizing the data, I mean like we could find a proportion, like the proportion of times that we got heads when we flipped a coin, or the proportion of people that are going to vote for a specific candidate in an election. Okay, or it could be the average height of everyone in this class. It's some number that's going to summarize the data. The sample size is just how many observations you have in your sample, or how many observational units. So the point of statistics is that we want to use statistics to estimate our parameters. So we can't get data on the entire population, so we collect data on our statistic, and then we use that to draw conclusions about our entire population. That's called statistical inference. So just a little graphic to remind you, the population is the bigger set, sample is a smaller set, parameters go with populations, you can tell they both start with P, statistics go with samples, they both start with S. So for example, an investigator wishes to know what proportion of voters in the US will vote Republican in the next election. So the population would be all the voters in the US. The parameter would be the proportion of all those US voters who vote Republican in the next election. So this investigator, she can't collect data on all the voters in the US, so instead she takes a random sample of 100 US voters and found that 40% said they would vote Republican. So the sample is that 100 US voters. The statistic is 0.4. That's the actual proportion that voted Republican in the sample, and the sample size is 100. So let's try another example. A real estate agent wants to know the average length of time a home in Cache Valley took to sell for the past year. So what is the population? The population would be all the homes that sold last year in Cache Valley. The parameter would be, well, let's see, she wants to know about the average, so it would be the average time to sell for all the homes last year. But we don't know what the actual average is because she doesn't have data on it. But she did take a sample of 50 homes and she found that the average length of time was 15 days. So what is the sample? The sample is the 50 homes that she collected data on. The statistic is the sample average. So the sample average of 15 days. And what is the sample size? It's just how many homes did she look at? She looked at 50 homes. And just a little thing to throw in here, what do you think her best estimate would be of the population average? Well, it makes sense to me that my best estimate of the population average would be the sample average, so 15 days. Now there is more to that. We're going to learn later how to do things like find confidence intervals and how to be more accurate or more precise in our estimates. But for now, the best estimate I have of the population average is that it'll probably be about 15 days. So let's say we have a coin that we know is not fair because it was damaged. We want to find the true probability of getting heads. Now this is a random process, not a typical population, like it's not a set of people or items. Okay. So when we say what is the population, it would be the results of infinitely many tosses of this coin. And the parameter would be the percentage of heads for those infinitely many tosses. The percentage or the proportion, like we can do percentage or proportion. Again, people just like percentages better. It just feels better to us, I think. But we can use proportions as well. Let's see, so let's say we flip the coin 1,000 times and get 300 heads. So what is the sample? It would be the 1,000 coin flips. What is the statistic? It would be our sample proportion. And what was our sample proportion? It was 300 out of 1,000. So that is going to give me 0.3 or 30%. What was my sample size? Well, it's just how many times did you do it? How many times did you collect data? 1,000. And what is her best estimate of the population proportion? Well, the best estimate of the population proportion would be our sample proportion. So 0.3. That's our best guess for the true probability of heads on this damaged coin. Now there are official symbols for parameters and statistics. Okay. So we're going to use a proportion anytime we want to summarize categorical data, and we use means or the average to summarize quantitative data. So if you have the average for your population, we're going to call it mu, and we'll remind ourselves of that back when we actually study averages. And the sample average would be this x bar. Okay. But we're not going to do averages for a little bit. We're going to focus on proportions for a little while. So the population proportion they called pi because that is the Greek letter that would go with a p. And our sample we call p hat. So in statistics, we're going to use English letters with symbols on them for our samples, and we're going to use Greek letters for our populations. So pi went with p, that's why they picked pi. So this is pi. We say pi. And the P with the little hat on it we call P hat. So sometimes on Canvas, if it won't let us do the symbols, you'll see us just write those out. But that's also how I will say it, so you know what I'm saying. And the population size is capital N. Usually we don't know that. You won't see that very often. But the sample size being little, lowercase n, you're going to see that all the time. So let's go back up. When I said that my sample proportion was 0.3, I could say that right here. So what was my statistic? That was my sample proportion. So I could have said p hat equals 0.3. Okay. And when I talked about my parameter, I didn't actually know what that was, but it would be called pi. I don't know the number, but it would be called pi. Let's see, and just a remark, a proportion, we've said it, a proportion is just a percent or a fraction written as a decimal. So like 40% is written as 0.4, or 2/5 could be written as 0.4. So just means you write it as a decimal. So let's read through each of these and decide if it sounds like they're talking about a parameter or a statistic. And let's summarize each with the correct notation. So 10% of senators voted for the latest bill. So do we have information on all the senators? Well, yes, there's not actually that many senators. We can actually collect information on all the senators. So to me, that sounds like it's for the entire population. So the senators is the entire population of senators. And so this would be a parameter. And I could say that pi equals 0.10. So pi is our population proportion symbol. Let's see, now the chance of heads is 50%. It didn't tell me this was for a specific sample, that we only did it 10%, like 10 times or 100 times or 1,000 times. If they don't tell you the size of the sample, that's a clue that it's probably going to be the entire population. So again, this would be a parameter. And I would say that pi equals 0.5. Let's see. 71% of Americans feel like in-person early voting should be made easier. Well, that sounds like a parameter until you keep reading. So it comes from a polling institute, those are people that take samples, of 801 adults. So that's a sample of 801 adults, which means that the number has to be our statistic. So my statistic, which we're going to write p hat, is equal to that 71%, so 0.71. Okay, let's see. The probability of rolling doubles is 1/6. Again, it didn't tell me what my sample size was, so that's probably just in general, or for all of my possible outcomes, all of my infinitely many rolls. So I'm going to guess that's my entire population, so that'd be my parameter. And so pi equals 1/6, or if I divide that, it'd be 0.16666. Let's see. Buzz pushed the correct button 15 times in 16 attempts. Oh, 15 times in 16 attempts. That sounds like it's a sample. Or specifically a sample of 16 attempts. Which means then my number here is going to be a statistic. And so it'll be a p hat, and I'll do 15 divided by 16, which equals, that one I don't know off the top, 0.9375. Okay, this next one. He rolls doubles 53 times in 100 rolls of a pair of dice. Okay, notice the difference between 4 and 6. So on number 4, it just said the probability of rolling doubles. It didn't tell us how many times we did it. Now it's saying we did it 100 times. That would be an actual sample. So that's a sample of 100 rolls, which means my number here has to be a statistic. Specifically, p hat equals 53 out of 100, or if I write it as a decimal, 0.53. Let's see, the next one. The average GPA of all incoming freshmen at Yoshi is 3.61. So that all tells me that's the population. It would be a parameter. So we'll use pi equals 3.61. Let's see, the proportion of times the buzz pushes the correct button in the long run. So we're talking about if you did it infinitely many times. So that's the population, so that would be a parameter. It didn't tell me what that number is, so we'll just leave it as a blank pi. Let's see, the average caloric intake of 31 teens who are sleep deprived. 31 teens doesn't sound like all teens in the world, it just, or even in the US, or even in Utah, or even at our college, it sounds like it was just a sample. So I think it's a sample, so I would call it a statistic of p hat equals, oh, no, it talked about average. Okay, and so if you go back to our symbols, when we use average and it's a sample, it's going to be X bar. And it didn't tell me what it is, so we'll just leave it as X bar. Again, we'll do proportions for the next chapter, then we'll learn about doing averages. Let's see, so chance models, officially. A model is a formal representation of a real-life process based on a set of specific assumptions. We've been doing this in all of our simulations, we're just giving official names. So a chance model is, we're just going to say that, let's represent this process, assuming anything happening is just chance. Okay, and it makes more sense to just see it in examples. So in this example, we know that some animals, like dogs, are known to have a keen sense of smell, but what about humans? So a woman from Scotland, Joy Milne, claimed the ability to determine whether a person had Parkinson's disease based on the person's smell. Let's see, as her husband died from Parkinson's, Milne noticed a different smell than prior to the diagnosis. To test her ability, researchers had 6 people known to have Parkinson's disease and 6 people believed not to have the disease wear t-shirts for a day. The t-shirts were collected to test Milne. Milne correctly identified 11 of 12 t-shirts as belonging to the person with or without Parkinson's disease. So we want to know, our research question here is, can she correctly identify whether a person has Parkinson's disease by smell, or was she just guessing? So what are the observational units? The units would be each t-shirt. And what is the variable? The variable is, let's see, Can she identify it? Let's see, the shirt correctly. And it's yes or no. She got it correct or not? So, yes or no. So if we want to classify it, because that seems like categories, not numbers to me, it would be categorical. And if we wanted to be even more specific, there's only 2 options, so we would say binary. So let's assume that she is completely guessing. So what would be our probability of guessing correctly on one shirt? It would be 0.5. So what we're going to do is we're going to have a model here, assuming that she's guessing, which means we're going to assume the chance of her getting each one correct is 0.5. So what are some possible chance models that could help us simulate her randomly guessing? Well, we could flip a coin. Heads means she's correct. You could repeat it 12 times because she smelled 12 shirts and count the number of successes. Or you could roll a die and we could say like 1 to 3 if she's correct. That means 4 to 6 if she's wrong. Repeat that 12 times, count the number of successes. You could use cards, spinners, etc. A lot of the things you can do as long as you make sure the chance of a success is 0.5 on each repetition, and then you have to do it 12 times. But instead, we're going to use the ISI applets. So if you go to your applet page, where we want to go categorical and 1 proportion, we're going to use this one a lot for the next month. And let's figure out, what do we need to put in here? We need to have the probability of heads, number of tosses, and number of repetitions. So if we think about it, what do we need for our probability of heads? The chance of her guessing correctly is 0.5. The number of tosses, how many things are in 1 repetition? She needs to smell 12 shirts, so we'll do 12 tosses. And for number of repetitions, we said in this class you should always do 1,000. If you want to have better chances of not accidentally getting something wrong on the homework, I like to use 10,000. This applet is actually really fast. Doing 10,000 shouldn't slow you down much. So probability of heads is 0.5. Number of tosses is 12. Number of repetitions is 10,000. And we draw the samples. Okay. So it says she was correct 11 out of 12 times. Looking at the histogram of the possible results of her guessing 12 times, how likely do you think it would be for her to guess correctly 11 out of 12 times? So if you look at it, this is my 11. Does that seem very likely? Doesn't seem likely at all. And similarly, the 12 would be even like more unlikely. Okay, but 11 doesn't seem likely at all. So the applet can give us a probability of her randomly guessing correctly 11 out of 12 times. So instead of just having to look and say, oh, there's not very many that were 11 or 12 that she could get correctly just by guessing, I can actually find the probability of that happening if she was just guessing. So we're going to look for the probability of her randomly guessing correctly 11 out of 12 times or more, because 12 times would be even more convincing. So we come back to our applet, and we've already put in everything up above. Now we just need to say that we want to count our samples as extreme as 11. We have this as a greater than because we want 11 or anything else to the right. Okay, and we'll click on count. And I got about 0.003 if we round, just because every time I do it, it might be slightly different. So we counted samples as extreme as 11, and the probability, I'm going now to 0.003. Now please make sure that you always follow along on the applet yourself so that you get good at using this, because you're going to be using it on the homework and exams. So what do you think? Does it seem plausible that she was just randomly guessing? Okay, so let's think about that. If she was just randomly guessing, okay, then there's only a 0.003 chance that she could guess correctly on 11 or more shirts. And so I say, well, that's a really small chance. That just doesn't seem plausible that she would get 11 or more shirts correct if she was just randomly guessing, because there was only a 0.003 chance that that would happen. That doesn't seem plausible. So I would say not plausible. Okay. And then I have to make a choice here. Based on that evidence, do I think she was just guessing? So no, I don't, because it doesn't seem plausible. So I don't think she was randomly guessing. So we looked at the evidence, we made our choice based on the fact that it didn't seem plausible. So we're going to use a vocabulary term called statistically significant. Our results are statistically significant if they would happen less than 5% of the time just due to chance. So less than 5% of the time just from chance. So in our example with the t-shirts, there is a 0.003 or 0.3% chance that she could randomly guess 11 or more times correctly out of 12 attempts, okay, if she was just randomly guessing. So are our results statistically significant? Well, 0.3% is certainly less than 5%. So yes, because it's less than 5%. So is our chance model a plausible explanation for the data? Do we think this just happened by chance? Well, no. We don't think that her guessing was a plausible explanation. So now there's something called the 3S strategy that our textbook likes to do. So basically it takes everything we've been doing and it just formalizes it. So our 3S strategy is just a way that we can use a chance model to measure the strength of the evidence against whether things happen by chance. We do all this during the step 4, which is draw inferences beyond the data of our 6-step process. So our 3 S's are statistic, simulate, and strength of evidence. So first we compute a statistic from our observed sample data. Then we repeatedly simulate values of the statistic that could have happened if it was just happening by chance, if we were just randomly guessing. And then we look at the strength of evidence. Okay, so we say, okay, well, based on how likely it was to happen if they're randomly guessing, we get to say whether or not we think that the chance model was true, whether or not we think they were just guessing, or whatever the situation might be. So in Milne's example, the statistic was that she was correct 11 out of 12 times. You could say that the count was 11 correct out of 12. So we can count it as a number, or you could change it to a proportion. So as a proportion, remember, a proportion is just a percentage, but you don't change it. Or it's a percentage, but written as a decimal, so you don't have to times it by the 100%. So we just do 11 divided by 12, or 0.9166. So we could have looked at it as a proportion instead of a count. Okay. Then you simulate. So we flipped a coin 12 times and counted heads. That count is our statistic. And we repeated that thousands of times. So coming back to our applet, every time we flipped the coin, it added a new dot to here. So it added a new statistic that we had simulated. So one time we flipped the coins and we got 3 heads, and another time we got 9 heads. And each time we put a little dot there. Then we look at the strength of evidence. So we found the chance of getting 11 out of 12 or more correct if she was just randomly guessing. And that was 0.003. So that tells me that there is a, oops, I didn't change that one, 0.003 chance that she could get her statistic if the chance model is true. Let's talk about a few cautions. So a statistically significant result cannot prove that the chance model is wrong. A statistically significant result can only suggest that the chance model is not plausible. And we do pick those words very carefully. Okay, and so not getting significant results does not mean that the chance model is right. It just means that the chance model is plausible. But there could still be something else happening. We just don't have enough evidence to know for sure. So let's come up and look at this one specifically again. So we got a statistically significant result in Milne's example, 0.003. So we had a small p-value. We can't prove that the chance model was wrong. Okay? So even though there was a 0.003 chance that she could just correctly guess 11 out of 12 times correctly, we can't prove that that didn't happen. People win lotteries. Okay? Things happen that have astronomical odds against them. She could have correctly just randomly guessed. So we haven't proved anything. We're pretty sure she didn't randomly guess, but we can't prove it. So never write that you've proved something in a statistics class. Okay. And on the opposite side here, if we don't get significant results, that doesn't mean that the chance model is right. It just means we didn't find evidence against it. So pretend, what if it had been a 10% chance she had guessed correctly, or of guessing correctly? Would 10% prove that she was guessing correctly? No, it doesn't mean that she was just guessing. Maybe she still can't tell the difference, okay? It just means that, oh, it's plausible that she guessed. We just don't really have enough evidence to know for sure. Okay. So in Milne's example, there was only a 0.003 chance of her getting 11 out of 12 correct if she's just guessing, but that's still possible. She could have just been very lucky that day. Okay, but again, her guessing definitely doesn't seem to be plausible. And a famous quote is that an absence of evidence is not the evidence of absence. So just because you don't have evidence for something doesn't actually mean that like you have evidence that it didn't happen. Let's say we want to consider whether or not there were any Vikings in America. Okay, so we now have research that says they were here. But let's consider back when people first came to America in, say, like the 1500s, 1600s. And if they didn't find any artifacts left behind by the Vikings, they would have thought that no Vikings ever lived there. Okay, or in other words, they didn't have any evidence that Vikings lived there. However, that doesn't mean that they found evidence that there were no Vikings. It just means they didn't find evidence that there were Vikings. But there's a difference between no evidence that there were Vikings and evidence that there were no Vikings. As it turned out later, there were Vikings here. We found evidence later. We just didn't have any evidence then. Or let's consider this example of whether or not a skunk has been in my yard overnight. So the null would be that there's no skunk in the yard because there's not usually skunks in my yard. The alternative is that there was a skunk in the yard. So if I check in the morning and I don't find any evidence of a skunk, does that mean that there was no skunk in my yard? Well, it's very plausible that there was no skunk, but I don't know for sure. The skunk might have just not left any evidence. So the fact that I don't have evidence that was a skunk is not the same as having evidence that there wasn't a skunk. So to truly know if there wasn't a skunk, I would have had to have video cameras over my entire yard all night to make sure that there was no skunk. Okay, let's see, what about the other way though? What if I check in the morning and I find skunk fur? Does that prove that there was a skunk in my yard? Well, there was probably a skunk. I have evidence there was a skunk, but I could still be wrong, like maybe a dog left the fur in my yard. So evidence can still always be wrong. In statistics, we're just dealing with probabilities. We can tell you what it was likely, but we could still be wrong. Okay, so let's say we rule out random chance. What does that leave? So our goal of statistical significance is to rule out random chance as a plausible or believable explanation for what we have observed. But we still have to worry about how well the study was designed and conducted. So the 3S strategy only lets us rule out random chance, but there could still be lots of other explanations depending on how well we design and conduct the study. So in Milne's example, what are some other possible explanations? So one explanation is she can actually tell whether or not a person has Parkinson's by smelling their shirts. Okay, that's the one that we're kind of hoping is true. That's our research question. That's our alternative hypothesis. Sorry, we haven't learned about that yet. We will next. But maybe someone secretly told her which shirts were which. Okay, maybe the person that handed her the shirts had different facial cues based on which type of shirt it was. Maybe she saw the patients wearing the shirts during the day and could tell who had Parkinson's just looking at them visibly. Or maybe she's actually smelling the medication for Parkinson's on the shirts, not smelling their body odor, but their medication. Okay. So what we want to do is we want to design the study really well so that hopefully the only plausible explanation left is the one we want to show, the research question, that she can actually tell whether or not a person has Parkinson's by smelling their shirts. Now, in this class, we'll assume that all of our studies are well designed. When you go out into the world and you're reading research articles, I highly suggest you go through and read how the study was designed before you trust the study, because not every study is designed well. Let's see, so this is an experiment about Doris and Buzz. So in the reading, Dr. Bastian did an experiment to see if Doris and Buzz, two dolphins, could communicate. In his first experiment, Buzz pushed the correct button 15 out of 16 times. If in that experiment we found only a 0.002 probability that Buzz could push the correct button 15 out of 16 times, if he was just guessing. Now, Dr. Bastian thought it was possible that some light leaked around the curtain, and that was helping Buzz know which button to push. So he decided to do a second experiment. This time, he replaced the canvas curtain with a plywood board. This time, Buzz pushed the correct button only 16 out of 28 times. Okay. And you can see we summarize it in this bar chart. He was correct the 16 out of 28 times, or if you change that to a proportion, it was somewhere around like 0.58. We'll calculate that exactly. So first, what is the statistic? That would be our sample proportion. And we need to actually calculate it. So we'll use our notation of p hat. And that's our 16 divided by 28, or 0.57. Let's see, now what is our sample size? How many times did we do it? 28 times. So let's use our 3S strategy to see if it's plausible that Buzz was just guessing. So our statistic is that he was correct 16 out of 28 times. Now we simulate it. We're going to flip a coin 28 times, count the successes, and repeat this thousands of times. Okay. We chose flip a coin because if he's just guessing, then that means you'd have like a 0.5 chance of getting it right or wrong. So just guessing, 0.5 chance to guess correct. So we can use the coin. Let's see, strength of evidence. Then, so we want to figure out what was the probability that Buzz could get the correct button 16 or more times out of 28 times if he's just guessing and it's just chance. So let's come down. I simulated what we need to put into the applet. So you need to have your probability of heads is 0.5, 28 tosses. I like to do it 10,000 times. And I want to count my samples as extreme as greater than or more 16. Okay. And you can see it highlighted everything from 16 on over. And it told me that happened about 29% of the time. So the probability that this could happen was 0.2938. Let me pull up the applet just to show you. So my probability of heads is 0.5. We're doing it 28 times. I'm going to do it 10,000 times, so I'll click draw my samples. Okay, and I wanted to do anything as extreme as 16. And looks like this time we got 28.68. Okay, again, every time you simulate, you'll be a little bit different. We're just hoping that we're all pretty close to somewhere around like 0.29. Okay. If you don't like this fact that it changes a little bit each time, you could do 100,000 tosses. Theoretically, we would want to do like 1,000,000 or 1,000,000,000 tosses, but that does take a while. Okay. So only about a 29% chance that he could get the correct button 16 or more times if he's just guessing and it's just chance. Well, is that plausible? So I like to write 29.38%. To me, in my mind, that makes more sense. Oh, I'm like, oh, 29% chance he could get that if he was guessing. Does that seem plausible? Yes. Completely plausible. I'm not going to be suspicious if someone tells me something can happen 29% of the time and then it happens. I'm not suspicious at all. So are my results statistically significant? No, because it was less than 5%. Sorry. Statistically significant means it's less than 5%, and in our case, it was greater than 5%. So it's not statistically significant. Let's see. So if we scroll down, that means we've said the chance model is plausible because we had a high probability of getting our results. If he was guessing, that means it's likely enough he's guessing. But we still don't know for sure. Maybe they're communicating, we just don't have evidence to say they're communicating. So we do not have evidence against the chance model, and we do not have evidence that he isn't guessing. Okay. There could still be other explanations that are possible besides guessing. We just don't know. Okay, but in this case, we don't have anything to say that he's not guessing. Now, you might have noticed that was conflicting results. Okay, so in our first study, we said there's no way he was guessing. But now it seems plausible he is guessing. So which is it? Okay, well, it's not uncommon to get conflicting results. This can happen from poor study designs or just from the luck of who's in our sample. Okay, maybe Buzz is just having a bad day or feeling sick. Or maybe, like on the first study, they really could see light around the curtain. And that's how they were doing it. Okay, so maybe he was right to try the plywood board. So really, what we like to do is think of each study as just one drop in a bucket. To truly make decisions, we like to look at all of the studies put together and see what the overall consensus is. Now, in step 6 of our 6-step process, we're supposed to look forward and ahead. And in fact, Dr. Bastian found out that when he put the plywood up, the equipment was actually malfunctioning, and the food dispenser for Doris didn't operate. And so Doris wasn't receiving her fish rewards during the study. Okay. And so because she wasn't getting her rewards, she stopped doing what she was supposed to. Okay. And so she wasn't communicating Buzz, so Buzz was really just guessing because she wasn't getting her fish. So he fixed the equipment, ran the study again, and this time he found very convincing evidence again that Buzz was not guessing. So here's an example with all 6 steps put in. So do sea lions understand when a human points at something? An Austrian study was completed to determine if untrained sea lions could follow various experimentally given cues when given a choice of 2 objects. So one cue was that they would point at the objects, and then the sea lioness would come and choose an object. So she successfully chose the pointed at object 37 out of 48 trials. So experimenters wondered whether the results show that Zwerg can correctly follow these specific types of directions more than 50% of the time. Okay. Because at 50% of the time, we would assume guessing, but they were just guessing. So guessing would be 50%. So step 1 is state the research question. In this case, it would be, do sea lions understand when a human points at something? Okay. Step 2 is design a study and collect data. Okay. So they had the Austrian study, and they would point. So Zwerg successfully chose the object 37 out of 48 times. So first of all, what is the variable unclassified? So it's whether did they choose the correct object, yes or no. Okay, this isn't numerical, this is category, so we'll say categorical. Only 2 options means binary. And I don't think it's stated anywhere specifically in the book, but the reason we care about this is if it's binary, if it's only 2 options, yes or no, then we can use proportions to summarize it. Okay. So everything we do for the next month will just be based on proportions and this binary data. Okay, so what are the observational units? It would be, let's see, each set of 48, or let's say each of the 48 pairs of objects, or each choice. So every time she makes the choice, she makes the choice 48 times. Let's see, how many observational units? Well, there's 48 times that she did it. What's the sample size? 48. So sample size means the same thing as how many observational units. Then we explore the data. So she was correct 37 times and incorrect 11 times. So you can see in the bar graph, if I do the frequency, which is just my counts, she was correct 37 times, wrong 11 times. Okay. Or you could change it to a percentage. So she was correct about like 78% of the time. Okay. And then it asks what percent of the time was she correct, so we can actually figure that out. So 37 divided by 48 equals 0.77. Okay, and remember our symbol for that, our sample proportion is p hat. Or if I want to change it to percentage, 77%. Step 4 is we draw inferences beyond the data. So if the study is well designed and conducted, there are only 2 main possibilities left. Either Zwerg is randomly guessing, that's the chance model, or Zwerg can follow human cues when given a choice of 2 objects. So to decide which possibility we have evidence for, we use the 3S strategy. So first is our statistic. What is our statistic? It was that p hat equals 0.77, or my count of, what did we say, 37 out of 48 correct. So you can use it as proportions, or you can just look at the count. Okay, then we're going to simulate with the chance model. So we're going to go to our ISI applets again. So it's categorical, 1 proportion. Okay, you need to know the probability of heads. Well, if we're comparing it to guessing, guessing would be 0.5. How many tosses? She did this 48 times, and I'll do 10,000 repetitions. And we want to count our samples as extreme as what we got. So we'll do greater than or equal to 37. So we need 48 tosses. We'll draw my samples. I want to count as extreme as 37. Okay, so when we put it in, it tells us that the probability, or the chance of getting 37 or more, is only 0.0001. Okay. That seems really small. Now notice here where it says choose statistic, you can do the number of heads, or you can change the proportion of heads. And if you do it, it will automatically change your count into your proportion for you. So it's 0.7708, which is what we got earlier. Okay. Notice p-value looks exactly the same. Histogram looks exactly the same. The only thing that changes down here is the actual numbers. So instead of like going from 10 to 35 for the number of heads, it goes from 0.21 to 0.73 because it's the proportion of heads. So it doesn't matter whether you do counts or proportions, you get the exact same answers. Okay, so now let's look at our strength of evidence. So if Zwerg is randomly guessing, how likely are we to see a result of 37 correct attempts or more out of 48 trials? Well, our probability here that we found was only 0.0001. So not likely at all. So do you think it's plausible that she was just randomly guessing? Well, we know she got the 37 out of 48. There was only a 0.01 chance of that happening if she was guessing, so I don't think she was guessing. Okay, and are my results statistically significant? Yes, because it's less than 5%. Let's formulate our conclusions. So based on this analysis, are you convinced that Zwerg can understand human cues? So I'd probably say yes. I feel like there is lots of evidence that she is not guessing. So lots of evidence that she can understand human cues. And step 6, let's look back and ahead. So looking at the study in detail, are we convinced that nothing else was going on that helps Zwerg know which object to pick? And otherwise, was it a good study? Now, we don't really know that. We'd have to go back and look at the study details more. Okay. Let's see. If Zwerg can understand human cues, can all sea lions? Maybe it's just female sea lions. Is it only sea lions that were raised around humans? Can they understand other cues beyond pointing? We should do more studies with more sea lions. That's kind of what you put in your research paper.